Okay, we want to talk about a characteristic of exponential functions. One of the problems you had in your assignment was to do a graph of an exponential function, relabeled, and determine how long it takes it to double. Ask you to do 3,500 to 7,000, ask you to pick any old point and see how long it takes to double. So here, we have a graph of your basic exponential function. Pretty clear that this graph doubles as you go from here to here, and as you go from here to here. Because of course the value of the function is 1 here and 2 here, so it doubles, and 2 here and 4 here, so it doubles again. So here's your doubling time from here to here, here to here. Also from here to here you go from 1/2 to 1. From here to here you go from 1/4 to 1/2. Now, doubling is not confined just to the interval from 1 to 2, or the interval for, 1 to 2, or 0 to 1, or -1 to 0, or -2 to -1. If you pick any y value and double it, okay? So here's a y value. Here's a doubled y value. If the graph is accurate, and you go over here and try to find the value of x that goes with this value, then come over here and find the value of x that goes with this value, the doubling time is still going to be the same. So one statement we can make is that y equals 2 to the x doubles whenever x increases by 1. Okay, now let's apply this to the idea of an investment. $1,000 at 10% doubles in about 7.2 years. Now we can calculate exactly when it doubles if we can use logarithms, and we're going to see that shortly. But there's this thing called the rule of 72, where you divide 72 by your percent difference, your percent rate, and you get the doubling time. Now that doesn't always work, but for common interest rates it works quite well. Not perfectly, and we're going to see how to actually calculate it without the rule of 7, but just using this, I can sketch a pretty good graph of how an investment of $1,000 changes over 14 years, 14.4 years, 2 doubling times. And I do that by simply relabeling this graph. So if I relabel the x-axis to where this is still 0 here, and this would be, well, again, the exponential function doubles between here and here. If the doubling time for your investment is 7.2 years, then instead of 1 we would have 7.2. Instead of 2 we would have 14.4. Then of course we could go back in time, but that doesn't make a lot of sense with an investment that starts at 0, but maybe it didn't start at 0. Maybe 0 is just a time when you have a certain amount, when you have $1,000, but this thing has been growing for, a number of years. Okay, so whether these numbers are relevant to the situation or not, we might as well put them in there. Okay, so we change, of course, the labeling of the y-axis. So instead of 4, you've got 4,000. And of course here we had 3, you've got 3,000. Here you got 2,000. I'm not going to label 1,000, but you know it's here. It'll get messy because it interferes with the graph. It's probably going to interfere with something anyway. Anytime I label something, it gets in the way of something else. Okay, so here we have it. That's a model of your principal for that $1,000 investment at 10% annual interest. Now I haven't specified whether it's annual compounded annually or compounded continuously or what. Well, the rule of 72 is kind of approximate. So then continuous compounding versus annual compounding doesn't make that much difference. So the rule of 72 kind of applies as a very approximate rule, no matter how you compound the interest. A little better for some compoundings than others, a little better for some rates than others. Well, okay. So now we can see that if we have this y value and then the doubled y value, now what's this y value? This y value is between 1,000 and 2,000. It looks like about 1,300. Looks like the value here. And I'm going to say maybe that's 1,200. And this is 2,400. Because it's going to be doubled. Okay. So these 2 points would tell you when you hit 1,200 and when you hit 2,400. That is not all that accurate with the 1,200, but if you have an accurate graph, you could, it'll work. And you're going to find that, again, change in time here is about 7.2 years. Having relabeled the graph, if you want to know how much money you have at 10 years, you come over here, here's 7.2, here's 14.4, halfway between would be 10.8, that would be here, so 10 would be about here. So I'm going to make an estimate, I'll do that in red, so here's 10. Yeah, probably a little too far to the right, but you can be more careful than I am. So here's 10. You know, this graph estimates that in 10 years, my $1,000 is going to grow up to what? Looks like here's 2,000, here's 3,000. That looks like about $2,600 or $2,700. And of course you can compare that. Okay, so with the relabeled graph, y doubles whenever x increases. By 7.2. That's only approximate. That gives you the idea. And we predict that y is 2,700 when x equals 10. I don't expect that to be a particularly accurate prediction. It might be up by a couple hundred. We can check this by finding what? Well, $1,000 at 10% simple interest. 1,000 times 1.10 to the 10th for reasons that you should understand. Or 1,000 times e raised to the 0.10 times 10, which gives me, my estimate's a lot better than I thought. Hadn't thought this through, but 0.10 times 10 is 1. That's 1,000 times e, and that is approximately $2,700. Okay, this will come out a little less than that. You'll see how much difference the continuous compounding makes over the annual compounding. So, now you're going to have a problem like this. I'm going to give you a percent and ask you to do some relabeling and so forth. Now we're going to go on and talk a little bit about how you solve an exponential equation with logarithms.